All right, hello. We are going to begin Chapter 9 for physics, talking about impulse and momentum and the conservation of momentum, which will be Section 2. So impulse is a combination of force and time. So you apply force to an object for a certain amount of time, and that's the amount of impulse that that object will experience. And so we can write the equation for impulse using force times the change in time. And we know that force is also equal to mass times acceleration, and if we take acceleration and break it down, we get that acceleration is equal to the change in velocity over change in time. And so we can take this whole quantity, which equals force, and substitute that into our impulse equation, and we would get that the mass times the acceleration, which is change in velocity over change in time, times our change in time from our impulse equation. And what happens is that these change in times will cancel, and so we can also get an equation for impulse that is the mass times the change in velocity. And so that's going to relate when we talk about the relationship between impulse and momentum, which we'll get to in a minute. So we can have basically two different ways to describe impulse. It's either the force applied over an amount of time, or a mass and that mass's change in velocity. So predominantly we use force times change in time for impulse, and so if you would like the word version of that description of the relationship, it's the product of the average force on an object and the time interval over which that force acts on the object. Because impulse is force times the change in time, we know that force is equal to newtons, and change in time is usually equal to seconds, and so our units are in Newton second. If the force isn't constant, then you would use the average force or find the area under a force time graph, just like we have done previously with finding average velocity with a distance time graph or average acceleration with a velocity time graph. So these are some really cool shoes. I don't think that they've taken off in popularity, but as you can see, overall it's less of a force, but if you looked at the area under the graph, perhaps that might be, I guess it's going to be larger, but it's also extending it over a longer period of time. And so the purpose of these shoes is to reduce the impulse that you feel like if you're running or something like that. You'd look pretty weird by running, but maybe it would help if you had bad knees or something like that. Okay, we can also use impulse when we're talking about other types of activities like baseball. So we apply a force on a ball when we hit it, and that increases until the ball recovers its shape and then snaps away from the bat. And so we can look at this in slow motion. And so you can see that the ball hit the object, which could be a bat. In this case, I think it's just a wall, and it deformed the ball, and then it snapped back. And so that force is being applied while the ball was in that deformed shape. Okay, so the other part of this is momentum. And so momentum is this Greek symbol rho, which looks kind of like a fancy P, and momentum is equal to mass times velocity. So the product of an object's mass and its velocity. And so units for momentum are going to be a kilogram meter per second, because the units for mass are traditionally kilogram and the units for velocity are traditionally meters per second. And so we can put impulse and momentum together because they are related and have what's called the impulse momentum theorem. And so we can say that impulse, which is F delta t, is equal to the change in momentum. So remember, change is always final minus initial, and so we take the final momentum minus the initial momentum. Well, we know that momentum is mass times the change in velocity, which also we already talked about was another way to express impulse. So impulse and momentum are two different ways to describe kind of the same thing, using different variables. For impulse, it's mainly force change in time. For momentum, it's for mass change in velocity. Well, when we have an object, we're usually not changing its mass. And so usually the only part that's going to be changing then is the velocity. And so we can break this down into mv final minus mv initial. Well, you know mv final is momentum final, and mv initial is momentum initial. And so we get that impulse, which is force change in time, is equal to the change in momentum. So change in momentum is equal to the impulse acting on it. And momentum and impulse are vectors, just like force, and so sign does matter. And so we need to be in the same dimension, either x, y, or z, or if we're in 2 dimensions, we would need to break those into components, just like we would do for a force, which we'll look at in the second section. So a large change in momentum can occur only when there is a large impulse, since they are related. And the only way to get a large impulse is to either have a large force over a short period of time or a small force over a long period of time. So if we look at the example of a car crash, we know the momentum final is 0 because the object has come to rest, meaning V final is 0. And so we need a force that's going to bring it to 0. And this can oftentimes be a very large force over a short period of time, which would be very damaging. So airbags can make a crash better because it reduces the force by increasing the time interval over which that force is applied, which can often result in less damage to the person inside the vehicle. Okay, well, momentum is basically inertia in motion. If something has a lot of momentum, it's usually difficult to change its motion, either to get it to stop or to get it to start. So a large truck is much more difficult to stop than a smaller car if they're moving at the same speed, because the only other variable at play there is mass, and the larger truck is going to have more mass. And so it would have more momentum. So a moving object can have a large momentum if it has a large mass, a high speed, or both, since the equation for momentum is m times v. And so the least ideal would then be a very large truck that has a high speed, which if you ever drive up to the mountains, you see the truck runoff ramps. That's why they're there, because these trucks have very large momentums and can be difficult to stop. And so an object at rest then has no momentum because its V final is 0, and so then anything times 0 is just going to give you 0. Okay, so we know that a change in momentum is a change in mass or velocity because that's the equation for momentum. Now usually, like we said, objects' masses aren't going to change, and so we're usually only changing velocity. Well, a change in velocity is acceleration. And we know that in order to have acceleration, we need a force. And so the greater the force, the greater the acceleration, the greater the change in momentum. And this is how impulse and momentum are related, since impulse is force times change in time. The time that the force acts is then also going to be important. We talked about that with the airbags. And so the longer a force is applied, the greater the change in momentum. So impulse, which is force times change in time, is equal to the change in momentum, which is m times the change in velocity. So that's our impulse momentum theorem. That's going to be really key here when we're solving problems involving impulse and momentum. So to increase momentum, we need to apply the greatest force for as long as possible, F and delta t. And so this is why if you play any sort of sport like baseball or even soccer, they would have you swing the bat as hard as possible and follow through. So you're applying the greatest amount of force for the longest period of time. Same thing with soccer. When you kick the ball, you don't just kick it and then stop your leg. You follow all the way through. Extending this impact time will decrease the impact force. And so this is why a lot of dashboards, and this is also the airbag reason too, but before airbags we had padded dashboards because if you were in an accident and you hit that dashboard, now you're going to extend that impact time, and so it'll help lessen the force that you feel on your body. So let's think about a carpet versus a wood floor. If you drop a dish, will the impulse be less if it lands on a carpet than if it lands on a hard floor? Well, the answer is no. The impulse is the same for either surface because both the plate or the dish has the same momentum for each instance. So the same momentum change will occur. So it's going to experience the same impulse. What it's not going to experience is the same impact. Okay, so the force will be less for the impulse on the carpet because of the greater time of momentum change. But the overall change in momentum is going to be the same. It's just depending on how are we changing those force and time variables. So on the carpet, we're going to extend the time over which that force is applied, meaning it's going to probably be less likely to break because of that greater time that it's impacting or experiencing the impulse. So impulse and impact are different. Now, they're going to experience different impacts, but the overall momentum is going to be the same.
Impulse and momentum. Let's see what happens when we apply an impulse to an object. For this movie, we will apply an impulse to a baseball. Impulse is equal to the force applied to an object times the time the force is applied to the object. We will apply the force to the baseball with a bat, and the time will be the amount of time in seconds that the bat is in contact with the baseball. The impulse will be equal to the change in momentum of the baseball. The change in momentum is equal to the mass of the baseball times the change in velocity of the baseball. So the force applied to the baseball times the contact time is equal to the mass of the baseball times its change in speed. If you decrease the contact time of the bat on the ball, you will then decrease the change in velocity. This is what makes a bunt work. When applying the bunt, the ball touches the bat for a very short time, creating a small impulse. This leads to a smaller change in velocity for the ball. If you increase the contact time of the bat on the ball, you will then increase the impulse, which increases the change in velocity for the ball. This is why your coach always tells you to follow through. When you hit a home run, you try to swing your bat so it touches the ball as long as possible.
Okay, so the last part that we need to look at is angular momentum. Since we talked about rotational motion in Chapter 8, let's talk about how that rotation applies to momentum and impulse. So the angular velocity of a rotating object changes only if a torque is applied. And if we look at Newton's second law of rotational motion, which was traditionally based on just Newton's second law for linear motion, which is force is mass times acceleration, torque becomes our force, the moment of inertia becomes our mass, and our change in angular acceleration is our change in angular velocity over the change in time. If we rearrange this, we get torque times the change in time is the moment of inertia times angular velocity. And so this torque times the change in time becomes our impulse, or force change in time for linear, and our moment of inertia times angular velocity becomes our angular momentum, which we use the capital L as our variable for angular momentum. And this would be the same as our mass times change in velocity for our linear momentum. The units of angular momentum are a kilogram meter squared per second. Well, we can, just like we have an impulse momentum theorem for linear, we can also have one for our angular variables. And so torque times the change in time, which is our impulse, is equal to the change in momentum, or angular momentum, which is angular momentum final, minus angular momentum initial. If there are no forces, linear momentum is going to be constant. Okay, so if we apply this to an angular situation, if there's no torque, then angular momentum is constant. However, our angular velocity can still change even if we don't have any momentum. And so our moment of inertia depends on mass and the way it's distributed around the axis. Unlike when we look at momentum linearly, it's just mass times the change in velocity. But when we're looking at angular, our inertia does depend on mass and then the way it's distributed. It's because we have different equations for that based on how our mass is distributed around the axis. And what this means is that angular velocity can change even if the torque is 0. So think about a spinning skater. They can continue spinning even if there isn't an outside torque applied by the way that they distribute mass around their axis. If they extend their arms or pull their arms in, that changes their angular velocity. And so that's kind of the only thing that's really different between linear and angular. Right, we're going to complete these practice problems in class, but of course feel free to look at them on your own. And then here is the homework, which is also on your outline, including all the answers. Have a good day.